You are standing on the ground right now, or sitting or lying down, and something is holding you there. You call it gravity. You have called it gravity your entire life. Newton called it a force. Einstein called it curved spacetime. But in the last 3 decades, a small group of theoretical physicists have been quietly building a case that neither of them was describing the real mechanism. Not a force, not even geometry exactly, something stranger. Something that sounds, at first, like it belongs in a computer science lecture, not a physics one. They are arguing that gravity might not be a fundamental force of nature at all. They are arguing that it emerges, the way temperature emerges from the motion of billions of molecules you can't see individually. And what it emerges from is information, bits, the same basic unit that describes a photograph on your phone or a sentence in a book. If they are right, the apple didn't fall because Earth pulled it. It fell because the universe was doing something that looks, mathematically, exactly like a hard drive keeping its books balanced. That is the claim we are going to investigate today, case file by case file. The same way we investigate every mystery on this channel. Not by trusting the headline, but by tracing the evidence back to its source and asking whether it actually holds up. Consider for a moment how strange this actually is when you slow down and sit with it. Every physical sensation you associate with gravity, the ache in your legs after a long walk, the way a dropped glass shatters on the floor, the reason rivers flow downhill instead of up, all of it might trace back not to some invisible rope tugging matter across space, but to a bookkeeping process, a rearrangement of information, the same basic currency that makes up a text message or a digital photograph, quietly settling into a more probable configuration, the way scattered playing cards settle when you shuffle them long enough. If that sounds more like something out of a computer science department than a physics lecture hall, that reaction is exactly the right one to have. Because it's the same reaction most physicists had when the earliest hints of this idea started surfacing in the 1970s. And yet the trail of evidence that leads here doesn't come from internet forums or speculative documentaries. It comes from some of the most decorated, most mathematically rigorous physicists of the last half century, working independently, often skeptical of each other's conclusions, and arriving again and again at the same strange destination. Let's start with the world you already trust. Isaac Newton in 1687 gave humanity its first working model of gravity. 2 masses attract each other with a force proportional to their masses and inversely proportional to the square of the distance between them. It worked. It sent cannonballs where predicted. It explained the tides. It eventually put a spacecraft on the moon using math written down before electricity existed. Then in 1915, Albert Einstein rebuilt the picture from the ground up. In general relativity, gravity isn't a force reaching across space. It's the shape of space itself. Mass and energy bend the fabric of space-time, and objects moving through that bent fabric simply follow the straightest path available. A path that looks, from our point of view, like falling. This is the version of gravity taught in every physics classroom on Earth, verified by everything from the bending of starlight around the Sun in 1919 to the detection of gravitational waves by LIGO in 2015. By every reasonable standard, general relativity is one of the most successful theories human beings have ever produced. It has passed test after test for over a century, from the precise, otherwise unexplainable wobble in the orbit of Mercury to the tiny relativistic corrections engineers must build into GPS satellites, or your phone's location would drift by miles within a single day. When a theory survives that many independent, high-precision tests across more than 100 years, it earns a level of trust that few ideas in any field of human knowledge ever achieve. So here is the credibility problem the physicist we are about to discuss had to face. And it's worth being honest about it up front, because a real investigation doesn't hide the awkward part. If general relativity works this well, why would anyone go looking for something underneath it? The answer is that general relativity has a wall it cannot get past. And the wall is called quantum gravity. Every other force in nature, electromagnetism, the strong nuclear force, the weak nuclear force, has been successfully described using quantum mechanics, the physics of the very small. Gravity has not. When physicists try to apply the same quantum rules to gravity that work everywhere else, the math breaks down into nonsensical infinities. For nearly a century, reconciling gravity with quantum mechanics has been the single most stubborn unsolved problem in theoretical physics. And it was an attempt to understand that problem, not a desire to overthrow Einstein for the sake of it, that led researchers into the strangest corner of modern physics, the physics of black holes. In the early 1970s, a graduate student named Jacob Bekenstein was working on a problem that seemed almost like a philosophical trick question. If you throw something into a black hole, a book, a star, a cup of coffee, where does the information about it go? Classical physics said the information simply vanishes behind the event horizon, gone forever. But Bekenstein noticed something odd. The area of a black hole's event horizon always increases when matter falls in, and it never decreases. That behavior looked suspiciously like a law from an entirely different branch of physics, the second law of thermodynamics, which states that entropy, a measure of disorder, or more precisely, a measure of how much information is hidden inside a system, always increases in a closed system. Bekenstein made a proposal that sounded almost absurd to many physicists at the time. Black holes have entropy, and the amount of entropy is proportional not to the volume of the black hole, but to the surface area of its event horizon. Stephen Hawking initially tried to prove Bekenstein wrong. He thought the idea was flawed, even a little absurd. Black holes, by definition, were supposed to be the one place in the universe where information simply ceased to exist, swallowed whole with no way out and no bookkeeping required. Instead, in 1974, using quantum field theory, Hawking accidentally confirmed and extended the idea, discovering that black holes emit radiation and slowly evaporate, precisely as thermodynamics would demand. It's worth sitting with the irony of that moment. A brilliant physicist set out to dismantle a graduate student's strange proposal and instead handed it the strongest possible endorsement. A rigorous mathematical proof, built from an entirely different direction, that arrived at the same unsettling conclusion. This is the credibility stamp of this entire case file. Not a fringe blogger, not a self-published theorist, but two of the most rigorous minds in 20th century physics, independently arriving at the same conclusion through the hardest math available to them. Black holes behave like thermodynamic objects. They have temperature, they have entropy, and their entropy is written on their surface, not their volume. That last detail is the one that should stop you in your tracks, and it's the reversal at the heart of this entire mystery. Think about what entropy normally represents. If you have a box of gas, the number of ways you can arrange the molecules inside it, the information content of the system, scales with the volume of the box. Double the volume, and you roughly double the space available for hiding information. That's how information behaves in every system physicists had studied before black holes. But a black hole's information capacity doesn't scale with its volume. It scales with the area of its boundary, its event horizon, a two-dimensional surface wrapped around a three-dimensional space. It's as if all the information about everything that ever fell into the black hole is somehow encoded on the skin of the thing, not filling up the inside of it. In 1993, physicist Gerard 't Hooft proposed a name for this strange behavior, the holographic principle. The idea is that a hologram, the shimmering 3D image you can produce from a flat 2D piece of film, might not just be a clever party trick with lasers. It might be a clue about how reality itself is structured. 't Hooft suggested that everything that happens inside a three-dimensional region of space might, in principle, be fully described by information encoded on the two-dimensional boundary of that region. It's a claim that, taken seriously, undercuts one of the most basic assumptions most people carry around without ever examining it. The assumption that the inside of things is where the real substance lives, and the surface is just a boundary, a skin with nothing special about it. The holographic principle flips that assumption on its head. The surface, in this picture, isn't just where a region ends. It might be where the entire informational content of that region is actually stored, with the interior functioning almost like a projection generated from that boundary data. Leonard Susskind developed the idea further, and by the late 1990s it had moved from a strange conjecture to something physicists took seriously enough to test mathematically. The test came from an unexpected direction. In 1997, a young physicist named Juan Maldacena published a paper that would become one of the most cited papers in the history of theoretical physics. Maldacena showed, using a simplified model universe, that a theory of gravity operating in a certain curved space is mathematically identical, not similar, identical, to a completely different theory, one with no gravity at all, operating only on the boundary of that space, one dimension down. This is now called the ADS/CFT correspondence, and it gave physicists their first rigorous, working example of the holographic principle in action. Gravity, inside that model universe, was not a separate ingredient. It was something that emerged automatically once you had ordinary quantum information sitting on a lower dimensional boundary. If you had asked a physicist in 1990 whether gravity could be made of something else, most would have said the question didn't make sense. In the same way, it doesn't make sense to ask what color a Tuesday is. By 2000, after Maldacena's work, the same question had a mathematically demonstrated answer in at least one model: yes. The paper has since been cited more than 20,000 times by other researchers, an almost unheard of number in theoretical physics, and it effectively launched an entire subfield dedicated to exploring exactly how much of gravity's behavior can be reproduced this way, using nothing but ordinary quantum information sitting on a boundary one dimension down. This is where the case file escalates, because a working example in a simplified model universe is interesting, but it isn't proof that gravity behaves this way in the actual universe we live in. The person who tried to bridge that gap most directly was a Dutch theoretical physicist named Verlinde. In 2010, Verlinde published a paper with a deliberately provocative title, On the Origin of Gravity and the Laws of Newton. His argument, stripped down to its core, went like this. If entropy really does live on surfaces the way Bekenstein and Hawking's black hole work suggested, then you can imagine any region of space as being surrounded by a kind of informational membrane, a holographic screen. As matter moves closer to that screen, the amount of information, or entropy, associated with the screen changes. Systems in nature have a built-in tendency to move towards states of higher entropy. That's just the second law of thermodynamics again. The same law that explains why ice melts and why a dropped egg doesn't spontaneously reassemble. Verlinde showed that if you assume gravity is nothing more than this entropic tendency, matter being nudged toward configurations of higher informational entropy on these holographic screens, you can mathematically derive Newton's law of gravity from scratch, without ever assuming gravity is a fundamental force to begin with. He later extended the approach to derive aspects of Einstein's general relativity as well. In Verlinde's picture, gravity is what physicists call an emergent force, in the same category as pressure or temperature. No one thinks pressure is a fundamental ingredient of the universe. Pressure emerges from the statistical behavior of countless gas molecules bouncing around, and no individual molecule has pressure the way a planet has mass. Pressure only exists as a large-scale, averaged-out description of countless smaller interactions. Verlinde's proposal is that gravity might be exactly the same kind of thing, not fundamental, but a large-scale statistical shadow cast by information rearranging itself on hidden surfaces. Under this view, asking what is gravity fundamentally might be a bit like asking what color a single gas molecule is angry. The question applies at the wrong level of description entirely. Gravity, in this picture, doesn't need a graviton, a fundamental particle carrying the force, any more than pressure needs a pressure particle. It simply falls out of the statistics once you have enough information rearranging itself across enough surfaces. It's worth pausing here for the part of the investigation that a lot of viral science content conveniently skips, because leaving it out would turn this from an investigation into a sales pitch, and that's not what this channel does. Entropic gravity as a specific theory is controversial, and it has faced serious challenges. In 2016, a team of astronomers testing Verlinde's later predictions about galaxy rotation found that his model made testable claims about how stars orbit within galaxies. And while some observational studies found the predictions matched surprisingly well, others found discrepancies, and a decisive, universally accepted confirmation has not arrived. Some physicists have also pointed out technical problems with deriving general relativity's full equations from entropic arguments alone, and the broader theoretical physics community remains divided, with serious researchers on both sides. Peer-reviewed critiques published in the years following Verlinde's original paper have raised specific mathematical objections about whether entropic gravity can reproduce every known feature of general relativity, including some of the more exotic predictions that have already been experimentally confirmed, like the precise bending of light around massive objects. This is not a case of scientific consensus, quietly rewriting the textbooks while nobody's looking. It's a case of a legitimate, still open research program built on genuinely established results, Bekenstein's entropy, Hawking's radiation, Maldacena's correspondence, extending into more speculative territory that has not yet been confirmed or ruled out. A responsible investigation has to hold both of those facts at once. The foundation is remarkably solid, and the building still under construction on top of it is not yet finished. This is the moment for the reality check, the point in the investigation where we separate what has actually been demonstrated from what remains an open hypothesis. because that distinction is the entire difference between science and speculation dressed up as science. Confirmed repeatedly by independent researchers using different methods, black holes have entropy proportional to the area of their event horizon, not their volume. Confirmed. Black holes radiate and evaporate in a way that matches thermodynamic predictions. Confirmed. Within at least one precisely defined mathematical model universe, gravity can emerge entirely from a theory of information with no gravity built in, as shown by Maldacena's correspondence. Not yet confirmed, and still a live scientific debate, whether Verlinde's specific entropic gravity model correctly describes gravity in our actual four-dimensional universe, and whether it can fully replace general relativity rather than simply offering an alternative lens on some of its results. It helps to think of these four claims as sitting on a ladder of certainty. The bottom rungs, the entropy of black holes, the fact that they radiate, are about as solid as anything in modern theoretical physics gets, confirmed through independent lines of mathematical reasoning that converge on the same answer. The next rung up, Maldacena's correspondence, is rock solid within its own defined model universe, even though that universe isn't a perfect match for the one we actually live in. The top rung, Verlinde's full extension of the idea to explain gravity as we observe it around us, is the part still being tested, still being argued over in journals and conferences, still capable of being proven wrong by the next set of observations. So when a title tells you that scientists have proven gravity is information and not a force, the honest version of that sentence is more careful and, frankly, more interesting. Physicists have built a rigorous, evidence-backed case that gravity behaves as though it emerges from information encoded on hidden surfaces, and in at least one precise mathematical setting, they have shown this can be literally true. Whether it is true of the universe you're sitting in right now is one of the most important open questions in physics, and serious, credentialed researchers are actively working to answer it using data from astronomy, particle colliders, and pure mathematics. That is not sensationalism. That is what a genuine frontier of science looks like from the inside, before the textbooks have caught up. To understand why this question matters beyond academic curiosity, it helps to think about what's actually at stake. And this is where the human cost of the mystery becomes visible, because it isn't really about black holes at all. It's about whether we currently understand reality's most basic operating system. Every physicist who has spent a career on this problem has effectively bet a significant portion of their working life on the idea that our current picture of gravity is incomplete. That Einstein, brilliant as he was, gave us a description that works beautifully at the scale of planets and stars, but breaks down at the edges, at black holes, at the earliest moment of the universe, at the scale where quantum mechanics takes over. John Wheeler, one of the most influential physicists of the 20th century and a mentor to entire generations of researchers, including Bekenstein, spent his later years promoting a phrase that captures the emotional weight of this pursuit: it from bit. Wheeler's idea, articulated in the early 1990s, was that every physical thing, every particle, every field, every force, including gravity, ultimately derives its existence from yes or no questions, from binary information, from bits. He wasn't being poetic for effect. He believed, based on decades spent at the center of theoretical physics, that reality might be participatory and informational at its deepest level, rather than made of solid, independently existing stuff. Wheeler had spent his career surrounded by the strangest results in physics. He coined the term black hole itself, worked alongside Niels Bohr on the theory of nuclear fission, and mentored some of the very researchers, including Bekenstein, whose work we've traced through this investigation. When a physicist with that kind of resume spends his final working years pushing an idea as radical as it from bit, it's worth taking seriously as more than an old man's speculation. It reads instead like the considered judgment of someone who had spent a lifetime watching reality behave less and less like solid matter and more like a vast, self-consistent information system, one equation at a time. For a physicist to spend a career chasing that idea means accepting genuine risk. If entropic gravity or holographic emergence turns out to be a beautiful mathematical dead end, decades of work don't transfer neatly to something else. Careers in theoretical physics are built on citations, tenure decisions, and grant funding that increasingly favors research with a plausible path to experimental confirmation. Pursuing an idea this foundational, this far from immediate real-world application, is a quiet act of intellectual risk-taking that rarely gets the recognition given to more headline-friendly breakthroughs. The human cost isn't dramatic in the way a disaster or a scandal is dramatic. It's the slower cost of committing a working life to a question that might not be answered within that lifetime at all. Bekenstein himself, before his death in 2015, spent decades defending and refining the entropy bound he first proposed as a young researcher, watching it move from a controversial suggestion to an accepted pillar of theoretical physics, but never living to see the larger question of emergent gravity fully resolved one way or the other. That pattern repeats across the field. Graduate students choose thesis topics in this area, knowing the honest odds. Most will spend years producing careful, technically demanding work that may never lead to the kind of clean, headline-grabbing confirmation that turns a physicist into a household name. They do it anyway, because the question underneath all of this, what is space, really, and what is gravity actually made of, sits close enough to the center of how the universe works, that even incremental progress feels worth the career risk involved. And yet the bridge to now is more immediate than most people realize. Because this isn't purely abstract mathematics locked away in university basements. The tools developed to study the holographic principle and entropic gravity have already found real, practical applications far outside cosmology. Researchers studying the ADS/CFT correspondence have used its mathematics to better understand the physics of quark-gluon plasma, an extreme state of matter created in particle accelerators like the Large Hadron Collider. Because the same holographic techniques that model gravity emerging from information turn out to be useful for modeling strongly interacting quantum systems that have nothing to do with black holes. Some condensed matter physicists have borrowed holographic methods to study high-temperature superconductors, materials with potential applications in lossless power transmission and more efficient electronics. Meanwhile, observational astronomy continues to test entropic gravity's predictions against real data from galaxy rotation curves and gravitational lensing, the same kind of evidence that once confirmed general relativity itself. Astronomers analyzing large surveys of galaxies have specifically checked whether the way stars orbit at a galaxy's outer edge matches Verlinde's entropic predictions instead of, or alongside, the standard explanation involving dark matter, an invisible substance most cosmologists believe makes up the bulk of a galaxy's mass. The results so far have been mixed rather than conclusive, which is itself a meaningful piece of evidence, because it means the idea is falsifiable in the way real science demands, rather than being vague enough to explain any outcome after the fact. Space-based missions and next-generation gravitational wave detectors, expanding on the legacy of LIGO's 2015 detection, are gathering increasingly precise data about how gravity behaves in extreme environments. Data that could eventually distinguish between standard general relativity and its emergent, information-based rivals. Future detectors, designed with even greater sensitivity than the instruments that made the first detection in 2015, aim to capture gravitational waves from a much wider range of cosmic events, including the violent mergers of black holes and neutron stars across billions of light years. Each merger acting as a fresh, independent test of whether gravity behaves exactly as general relativity predicts, or shows subtle deviations consistent with an emergent, information-based origin. Meanwhile, theorists working on quantum computing have found unexpected common ground with holographic gravity researchers, because simulating a quantum system on a boundary and asking what bulk geometry it corresponds to turns out to be structurally similar to problems in quantum error correction, the technique quantum computers need to protect fragile information from being lost to noise. Some of the same mathematical language now shows up in papers about building more stable quantum computers, as it does in papers about the inside of black holes, a connection that would have seemed nonsensical to physicists working in either field only 20 years ago. This is not settled science waiting patiently in a textbook. It is an active, funded, ongoing area of research, with real telescopes and real particle detectors currently gathering the evidence that will eventually settle the question one way or another. So where does that leave the claim in the title, the one that pulled you into this investigation? Gravity doesn't exist as a fundamental force, and what pulls you down is information. Is that proven? No, not in the simple, closed-case way a viral headline wants you to believe. But is it a wild, baseless claim invented for clicks? Also no, it is a rigorously constructed hypothesis built on decades of confirmed results from some of the most respected physicists of the last 50 years, tested in precise mathematical models where it has already been shown to work, and currently being tested against the actual universe using real telescopes, real particle accelerators, and real mathematics that has nothing to do with speculation for its own sake. The honest answer, the one this channel exists to give you instead of a manufactured certainty in either direction, is that we don't yet know whether gravity is fundamentally a force, a curve in spacetime, or an emergent shadow cast by information. But we know, with real confidence, that the question is legitimate, that serious evidence already points toward the informational picture being at least partly true in principle, and that finding the full answer would rank among the most significant discoveries in the history of physics, on par with relativity itself. The apple that fell on the ground beside you this morning, the weight you feel in your own body right now, might ultimately trace back not to a pull reaching across empty space, but to the universe quietly balancing its books, the same way a hard drive keeps track of every file it holds. Except the hard drive, in this case, might be the fabric of space itself. It's a strange thought to sit with the next time you drop something and watch it fall without thinking twice about why. For your entire life, that fall has felt like the most obvious, most unquestionable fact in the universe. Something pulling, something pulled. The evidence gathered here doesn't erase that experience. It just suggests that underneath the falling, underneath the pulling, there may be a far quieter process at work. Bits of information settling into place, the way water finds its level, the way a shuffled deck of cards drifts toward its most probable arrangement without anyone forcing it there. Nothing about your daily life changes because of this. The apple still falls, your coffee still spills if you knock it over. But the reason why, the actual, deepest reason why, may turn out to belong to a chapter of physics nobody has finished writing yet. If a mystery like this is the kind of evidence-based reframing you come to this channel for, the case files continue every single day, each one built the same way this one was. Traced back to primary sources, checked against what's actually confirmed versus what remains open, and delivered without unearned certainty in either direction. Subscribe if you want the next investigation waiting for you, and if you already have a theory about where this evidence leads next, the comments are where that conversation happens. The universe keeps its books somewhere. We're still working out exactly where to look.